Today, we are going way, way back, deep into our evolutionary past, to uncover the origins of something we almost never think about, but absolutely cannot live without, our sense of balance. We're going to explore the vestibular system right from its very first spark of life.
Welcome! This is the first of a 5-part explainer on vestibular phylogeny, and it's brought to you by Australian Dizziness Clinics. Together, we're going to see how this incredible system was built, piece by piece, over more than 500 million years of evolution. So our mission here is to trace the vestibular system from its most ancient, single-celled roots all the way up to the very first vertebrates. And as you'll see, the fundamental building blocks of our balance system were put in place long before fish even ruled the seas.
So that begs the question, where does our sense of balance truly begin? The answer might actually surprise you. It's not in an inner ear or even in a complex animal. No, it starts with a single cell, and its original job had nothing to do with balance. It was all about finding food. Our story kicks off in the Precambrian era, with the cellular blueprint that would eventually give rise to the single most critical component of the vestibular system, the hair cell.
Okay, just look at this. The family resemblance here is absolutely stunning, isn't it? On the left, that's a Choanoflagellate, our closest single-celled relative. Now, see that collar of tiny filaments, the microvilli, and that central whip-like tail, the kinocilium? That whole apparatus was originally a feeding tool. It would beat to create a current and trap bacteria. But here's where evolution gets clever. This structure was ex-apted, a fantastic term meaning it was co-opted for a completely new function. That feeding collar became the sensory antenna of our modern vestibular hair cell. The tool for finding food became the tool for feeling movement. Just incredible. And from there, we get the first dedicated balance organ, the statocyst. It's such a brilliantly simple solution, and you find it in early invertebrates like jellyfish. Think of it like a biological snow globe, right? You've got this dense little stone, a statolith, sitting inside a fluid-filled sac that's lined with sensory hairs. As the animal tilts, gravity just pulls the stone down onto a new patch of hairs, signaling which way is down. Simple, but effective. And here is the absolutely crucial point for us as clinicians. The physical structures might look different, but the genetic recipe, it's incredibly ancient and deeply conserved. The very same gene families that build a jellyfish's statocyst, genes like PAX2/5/8 and ATO1, are the exact same ones that orchestrate the development of our inner ear. This isn't just some fun evolutionary trivia. It is a direct molecular link from these ancient life forms to the patients we see in our clinics. Understanding this shared toolkit is really foundational to where future genetic research in vestibular disorders is headed. Okay, so let's fast forward a bit. Let's see how this cellular blueprint and that shared genetic toolkit came together to form the very first vertebrate ears. And for that, we have to turn to the agnathans, the jawless fish. These creatures are basically living fossils, and they give us this incredible window into the early prototypes of our own vestibular system.
First up, we've got the hagfish. Now, at first glance, its inner ear looks incredibly primitive, and for decades, it's presented us with a really fascinating scientific puzzle. And this brings us to what's known as the One-Canal Enigma. For a long time, the old view is that the hagfish's single canal was the simple starting point for all other ears. It was seen as stage 1. But new genetic evidence has completely flipped that story on its head. It turns out the hagfish has a gene called OTX1, which in more advanced vertebrates is essential for forming the horizontal canal. So what does that mean? It strongly suggests the hagfish's ancestor actually had a more complex system. The modern hagfish here isn't primitive. It's been simplified over time, with 2 canal zones likely fusing into one.
And you can actually see the evidence of that fusion right here in its anatomy. See how it's a single kind of donut-shaped canal? But, and this is the key, it has 2 distinct sensory regions, the ampulla, one anterior and one posterior. So this isn't just a simple loop. It's more like a compact 2-in-1 sensor, which is perfectly adapted for an animal with a burrowing lifestyle and a compressed skull.
Now, our next key witness in this story is the lamprey. And unlike the hagfish, the lamprey's ear shows a really clear, definitive intermediate step. It has a true 2-canal system that gets us much closer to the 3-canal arrangement we're all familiar with.
So the lamprey has 2 vertical canals, an anterior and a posterior. This setup allows it to detect pitch, that's nose up, nose down, and roll, or tilt. It's perfect for stabilizing itself during its wavy, eel-like swimming. But what's it missing? The horizontal canal. And why doesn't it have one? Well, it doesn't need one.
As a jawless swimmer, it doesn't make those fast, pivoting left-right turns, the yaw movements, that become the hallmark of predatory jawed fish. Its anatomy is a perfect match for its function. Form follows function even way back then. Now, let's take a look at the otolith organs. Instead of a separate utricle and saccule like we have, the lamprey has this large, continuous sensory sheet called the macula communis, or common macula. And this is the crucial ancestral blueprint. It's from this single large sensory field that different regions would later specialize and separate, eventually giving rise to the distinct utricle and saccule we know. Understanding this common origin really helps us appreciate just how deeply interconnected the functions of those two organs still are today. So, after that whirlwind tour through deep time, let's just pause and pull together the key evolutionary takeaways from this very first stage of vestibular evolution. What are the big ideas to hold on to?
All right, here are the three big ones. First, the cellular blueprint for our precious hair cells was actually borrowed from the feeding collar of our single-celled ancestors. Second, the genetic recipe, the actual genes for building balance organs, is ancient and shared across vastly different animals. And third, the jawless fish show us this beautiful, clear, stepwise progression of the canals, moving from a fused system in the hagfish to a functional two-canal system in the lamprey, which perfectly sets the stage for what was about to happen next.
Because life in the ocean was about to change, big time. Join me in our next explainer video, Video 2, the Gnathostome Revolution, where we'll see how the evolution of jaws demanded a brand new sensory innovation, the horizontal canal.
Thank you for listening to this series. To explore more similar topics regarding dizziness, vertigo, and imbalance, and to get clinician and patient resource materials, visit AustralianDizzinessClinics.com. Please subscribe and leave a rating.